2016. And he previously completed his PhD from the University of Bonn in Germany, and in 2012, and he was a postdoctoral fellow in UC Berkeley in 2014. Joao has done a lot of very impactful work in multiple areas in computer vision, including image segmentation, object reconstruction and post-estimation, and action recognition and video understanding, proposing the Kinetics dataset for large-scale action recognition and multiple architectures for video understanding, such as the i3D or the parallel architectures for fast inference. Joao, thanks a lot for coming. We're looking forward to hear about your talk.
Thanks, Xavier, for inviting me, and it's a great pleasure to be here in such a reputed institution. My first time at MIT, kind of. I'll be talking about more general perception, some ideas we've been developing at DeepMind around this topic. So let me just get started. Okay, yeah, so the overall goal of many of us, including many of you probably, is to build robots that we can interact with and that are, generally smart and can understand the world around us as well as we can, so that we can communicate with them, interact with them, ask them to do things, and so on. An important component of this will be video understanding. So these robots need to really understand the video and the rest of their senses incoming into their perceptual system to achieve this. And yeah, I was thinking a little bit how hard this is, and how can we check if we have a good handle on video understanding. And one example of a test would be this: given a TV show, and I was watching recently this Umbrella Academy show, can we build a model, a perceptual model that can go through 2 seasons of this show? That there's only 2 seasons so far, times 10 episodes, and it can capture the characters, their personalities, their relationships. Can capture the main events, whether someone died and someone started a job and so on, and then we can query the model about all these things and get meaningful replies. So just to see how hard this is, just imagine one scene from this TV show where one of the characters gets possessed by a spirit. So this is the scene. So by just looking at it, a human can understand what's going on. So he's obviously getting possessed by a spirit, and now from now on, his actions are determined not by the original character itself, but by the spirit. So if you're trying to solve this challenge of understanding characters and the timeline of events and so on, you need to understand that this period where the character is possessed by the spirit, his actions don't define him. They must be attributed to the spirit. So this is fairly complex and very far from what we're doing right now in video understanding. Very, very far. So another opposite situation is when a character actually travels in time and actually ends up fighting itself, like an older version of itself. And in this case, if you want to understand that character, you need to understand that the character has two instantiations in this particular moment. So any actions they do, you need to factor them into the common character in order to understand their personality and so on. Again, very hard for current systems to get to anything remotely related to this. And so I wish we were spending more time thinking about these very complex problems. But what really happens in research in this area right now is that we're not using our brains much of the time. Much of the time, what's happening is we're just doing hyperparameter search, architecture search, and just waiting for our computers to get that little update in the validation curve. And we're really nervous there, just waiting and hoping that validation curve goes up. But it's kind of like an art, not so much a science, and mostly it's really like really searching. So there's no really sure way to improve architectures and so on. We need luck, and we need lots of computational resources to make progress in this area. So if you think about the different tasks people doing, for example, in computer vision, things like object detection, for which you have, say, mask RCNN and 1,000 variants, also other families, and each with its own 1,000 variants. Then let's say you want to do semantic segmentation, then you have a different architecture such as the UNet or fully convolutional networks. And there are thousands and thousands of alternatives. If you want to do object tracking, there's also a whole literature of different architectures for doing that. So my point is that every task comes with different architectures, and every time you think that there's a new task that should be proposed, there's a lot of effort just building architectures, tuning them, and that's probably most of the research we do in the end. So this is one thing. So having different tasks and all the architectural work that comes with that. Another dimension is different modalities. So every time you have a different modality, you also need to build a new architecture. And when you start combining modalities, it's even worse. Now you need to think how to put it together. For example, if there's any questions, just feel free to interrupt me at any time. Yeah, so for example, for audio, a common approach to fuse audio and video is to have, say, convnets for a 1D convnet or for audio, for example, and then a 2D convnet for video, and then you compute features, and then you need to fuse the activation somewhere in the middle, because the signals will be have different dimensions, so you need to do some work to fuse them. For example, a recent state-of-the-art model uses attention in the middle, and so this one by Fayak and Kumar, and then it computes kind of like alpha weights for each particular video to combine the modalities in a per video way. So also some work from DeepMind, objects that sound from Raleigh and Andrew Zisserman that explore different ways of doing fusion somewhere in the middle of the network. But any paper that does audiovisual fusion will do some exploration on architectures. And this is a lot of work. If instead of audio you want to fuse LiDAR and images, now that's a totally different setting. So one popular approach for self-driving cars is project the LiDAR point cloud into multiple views, say a front view and the top view, a bird view, and then have convnets for all of these. And then if you want to do object detection, you also need to add some kind of a region proposal mechanism. And again, there's like a whole new set of decisions, architectural decisions, to fuse the signals and to be able to do various tasks on these different modalities. So just one more example, if instead of LiDAR or audio, you want to do text plus images, again, there are very, very powerful systems proposed for this, but also very complex. For example, you may have a language encoder, a BERT language encoder, and then you have a vision encoder, and you put some heads on top for generating objects. You may have some cross-modal module, some decoders. Anyway, so I think this illustrates what's going on. That much of the research we do is driven by the modalities we consider and by the tasks we consider, and there's a lot of repeated work every time. And yeah, there's a bit this quadratic growth of architectures for any combination of tasks and modalities. And that takes a toll on the resources in the field. So the project around perceivers we have at DeepMind is to simplify this quite a bit and have one architecture that can handle any set of modalities and any kind of task, or at least most of the tasks that people care about. And the kind of setting we were envisioning is that there's an input matrix. There's a query matrix that defines the kind of tasks you're interested in. And then there's a module that computes some outputs for those queries. And so we have some work already under review trying to realize this whole vision. But for this talk, I'll focus on just a subset of that, just considering multiple modalities, but a single task. So there's a single output matrix. And so that's the outline of this talk. So I'm thinking about doing some motivation that I've done already, then doing a quick tour of some of the work in video we did at DeepMind that also motivates a little bit for this perceiver direction we're working on now. Then I'll go into details into the perceiver system, and then hopefully there's some time for discussion. So if there's some questions, again, feel free to ask them. or if you don't agree with some of the things I just said. All right, so I'll just continue with a quick tour. So we have one branch of our research on video models, which is about building models that are fast, that are large, and that are able to deal with long videos. So this is a big challenge in video because, you know, if you want to do that test with a TV show that has 2 seasons of 10 episodes, that's hours and hours of video, and the model needs to learn throughout the series to you know, understand the characters and so on. And yeah, it needs to have these very long range dependencies and so on. So we're interested in that. And one paper we had a few years ago was about reducing the latency of video processing. So this paper called Massively Parallel Video Networks. And the idea there is that we identified these very deep models that people process videos with. It's say a ResNet that has 40 layers. So these models have high latency because they need to do all these sequence of layers in sequence. So 40 layers, and they can't really parallelize all these layers, and they can't process them at the same time. So you need to like really start with layer 1, layer 2, and so on up until the end, and this may take a long time. Even though the video is barely changing, and yeah, and low latency is important because, say, you want to track a basketball player and you want to track the key points, this needs to be very fast. So one idea we had, very simple idea for being able to parallelize the processing of the various layers, if we have parallel resources, is the following. So let me just first explain what I'm showing here. So along the vertical axis, I'm showing the layers of a neural network. So let's say, and in the horizontal axis, time. So let's say you have image 0, and then you have 4 layers. So image 0 creates some activations for layer 0, some activation for layer 1, layer 2, layer 3, and then you have your output at the end of the network here is Y0. So this will take some time because the network needs to process in sequence these 4 layers. So our very simple idea here was to, instead of having these vertical arrows, we just have these diagonal arrows. And now what happens is that all the layers can process in parallel. Now the problem is that, of course, the last layer is not receiving activations from the corresponding image on that layer. But if we can train the model to predict the future, so let's say here, so let's say that the model sees image 0 and wants to predict Y3, then all the layers can be processing in parallel. And now if you have parallel resources, the latency will be very low. This all hinges on the fact that the network is supposed to be able to predict the future a little bit. And we did some more engineering on top of this, and we found that it's actually possible to get some decent results with lower latency in this setting. So later on, we generalized this idea a little bit into not just inference, not just testing, but also learning for cases if you want to do, for example, online training and want to do training in parallel and in a streaming way. And so the idea here is that, so again, I'm showing the network depth in vertical. So each of these little circles is a layer. And then on the horizontal axis, I'm showing the time. So as the model starts training on one particular frame, time never stops. So it goes diagonally like this, produces activations, all the way to the output where it produces some vectors, say. And then to do backprop, it needs to store all the activations for the various layers, and then given the activations for a layer and the gradients from the layer on top, it can compute the new gradients and update weights. So that's how backprop works. So it blocks the network a little bit. So it needs to finalize updating weights before it can compute new activations. And so one idea we have here, similar to the massive parallel paper, but now extended to training, is that instead of having to cache activations for all the layers, it just reuses the activations from the most recent frame. So if you see here these colors, so basically it's for each layer, it's reusing the gradient from the layer from above and just using the activations from the latest frame rather than caching activations from several frames apart. So this comes with very good memory savings because you don't need to cache activations, just reuse the latest ones, and it kind of works assuming that there's not a lot of motion. So which is usually the case. If you have like 25 frames per second, there's little motion, and this is a decent approximation. It's like a noisy version of backprop that is very memory efficient and fast. And then we had some further extension, the CAPR, that leverages skip connections to better model time. So I'm just skimming over this and won't go into many details, but if you're interested, check our CAPR paper this year or get in touch with me. And yeah, the main takeaway is that we can now train on much larger batches of videos. So if you see here on the right, using regular backprop with a long video, say 10 seconds long, which is already long for most models, you can train with a batch size of 1, whereas with this streaming training approach that doesn't cache activations, you can train with a batch size of 40 videos, or alternatively, you could train on a video much longer, say 40 times longer. Yeah, so perhaps our most well-known work out of DeepMind is in benchmarks, namely the Kinetics dataset and also the Kinetics dataset more recently. So the Kinetics dataset is a very simple dataset similar to ImageNet, where you have videos, 10-second videos from YouTube, and you have a single label for each video. And I know also that MIT has very good benchmarks like moments in time and hacks recently. So it's in that space. And yeah, we published it first in 2017. And we kept building upon this data set. So the first version in 2017 had 400 classes. Then we expanded to 600 classes, 700 classes, and then in 2020 to 700 classes, each with 700 examples. And then more recently, we did Kinetics, which I'll explain a bit later. And yeah, so we have also a yearly challenge on Kinetics. This year's winners were Byte and CMU. And let me just explain to you very quickly how this worked. The participants were only allowed to train on Kinetics and ImageNet, and they would produce a 500-dimensional feature vector per video, so rather than class scores. And what we did this year was we were training linear classifiers on top. So the main motivation for this was that now we would have features for the whole dataset and could do a bit richer analysis, like nearest neighbor analysis, that I'll show you next. Unfortunately, the participants still used large ensembles of models. We were trying to avoid this, but in the end, so the best participants would use like 10, 13 ImageNet checkpoints, combining ConvNets and VIT-based models and whatnot, and those end up getting the best results. But anyway, let me show you some of the analysis we did on the best method, just so you understand where the technology is right now. So here I'm showing a couple of videos. On the left is a test video from the test set, and on the right is the nearest training video in terms of the feature vectors that they provided to us. So yeah, no surprise here. Both videos are very similar, and the model does produce a correct classification of silent disco. This is one class of kinetics. So here's another very confident nearest neighbor from the winning model. Here again, very simple video, just stacking cups, the model gets correctly, and the nearest neighbor, it makes sense. Perhaps more interesting, the least confident nearest neighbors in this case is arguing, so the model still got this correct. And one more correct result. So this class is very meta. It's like it's called looking in mirror. It's basically people looking at themselves in the mirror, and the winning model got this right, even though it's very hard. Maybe it notices that there's some kind of like distortions in the mirrors and so on, or maybe the frame of the mirror, but the model got this right as well. And in terms of the wrong ones, maybe these are the most informative. Here, the nearest neighbor for playing maracas is catching fish. I guess you can understand this because of the motion is kind of similar. And maybe the videos are not very good quality, but still a fairly blatant error that, clearly the state of the art is not there just yet. it still produces very wrong results in some cases. And I have one more example, I think, of a wrong one. So in this case, on the left, you have people training a dog, whereas on the right, you have the child tiptoeing. And I guess in this case, the model has these two as nearest neighbors more based on the scene and perhaps the texture of the pants, and it's not really looking at what they're doing so much. So still plenty of space for improvement. Okay, now it's the final one. Here it's another nearest neighbor that is wrong. On the left, the class is making bubbles, whereas on the right it's cleaning pool. And I guess just because the overall scene is the same, the model thinks this is the most similar video. Okay, I put more videos in. I thought final wrong example, wrong classification from the model. On the left, it's cutting cake. On the right, it's barbecuing. But because the overall scene is fairly similar, again, the nearest neighbor is incorrect. Yeah, and the other benchmark we invested time in is AVA Kinetics. The goal there is go beyond classification and do some spatial temporal action localization. For example, instead of just saying that this is alligator wrestling, we also have boxes around everybody. In this case, like some people are sitting and watching, and one person is holding, in this case, the alligator and crouching. And our contribution there was to add many new videos to the AVA dataset that only had 400. So now we added like 240,000 videos from Kinetics, short ones, with a single frame annotated, whereas AVA, there are like 15-minute videos with annotations every second, and the videos are like 15 minutes long. Okay. Yeah, so that's it for benchmarks. Again, if anyone has questions, just feel free to ask them. Okay, if not, I'll skim very quickly over this architecture work we did. So the i3D model is a bit old by now. It's like from 2017, but I'll just explain very quickly the idea, which was to just adapt ImageNet classifiers, convnets to video by just inflating their filters. So from 2D to 3D. So if you had like ImageNet filters shown here in the bottom, expanded in time, so they're like always the same, and then fine tune them, you would get some kind of dynamic filters. And you could either fine tune them or RGB videos or flow videos and get different models like that. And there were many other models developed on Kinetics. The first few years it was convnets, but more recently this year, transformers. So like models like Timesformer, Vivid. Yeah, so Kinetics was impactful in developing some of these architectures, I find. And in terms of AVA models, the early ones would use also i3D, combined with some kind of region proposal network to get boxes around people, and then pull the i3D features inside those boxes. We did a bit of work there and participated in the first AVA challenge back in 2018. So this was work with Rohit Girdhar. We basically simplified the model, added a bit of augmentation, and got good results like that. So the dataset was recent at the time. And then we did some work on top of this and switched to transformers. So we had still the i3D trunk, but then to create the features for each box, we would use a transformer that would be conditional on every box, and then it would attend over the whole video contextually on that box. And I have some nice visualizations to show from that work. So it both worked well and it produced very intuitive attention map. So if you wanted to recognize what the person in the middle is doing that has a box around it, the model would attend to the other people, so shown here in red, the attention maps, and also to objects around them. So this was like fairly interesting visualization we got out of this, and kind of motivated us to pursue transformers further. And some of this ended up in the perceiver work I'll present a bit later. Yeah, and besides these architectures, we also pursued exotic tasks. And by exotic tasks, I'll give a couple of examples here. So, of course, we want to be able to do action recognition, but we also want our robots to not be scared of, say, a puddle in the sidewalk, right? Such as shown on the right. If the robot doesn't understand that the tree is shown on the floor on the right here, are a projection from the, are a reflection. They may be scared and just, block and not keep moving in the sidewalk. So it's important that, our models are able to, in some sense, disentangle these factors of variation, such as shadows and reflections and so on. And one approach we tried to deal with this is is kind of like a self-supervised approach, where we would generate millions of videos that are reflection-like. So by blending multiple videos with some factor of blending, we would create this kind of videos shown here on the left that combine multiple videos. And then we would train an encoder-decoder to separate them back. So the idea would be that if the model then sees a video that has some natural reflections, it can also separate them this way. It's like a way to get the free ground truth. And yeah, in some cases it did work. Like for example, in this video where you have a car, someone is driving and there's some trees, and you have this the trees reflected from the windshield, and you could see that the model would do well in that case, or at least decently well. There's still a little bit of artifacts on the left, on the bottom, I mean. But yeah, obviously not all videos are pure reflections like this, and there's areas that have reflections, areas that don't have reflections. Then we still did a follow-up work on this, that is an audiovisual version. And the idea here is that maybe there's a scene with some reflections, and we want to be able to control which of the layers to output based on some control signal, in this case, audio signal. So let's say that on the left, we have this blended video. And let's say that there's a piano sound that the model is receiving. And then the goal is for the model to produce just a video of the piano. And on the right, the same, but now the sound would be the person singing. So the model should be able to control its attention and return the layer having the person singing. Again, this is a multimodal architecture, so we put quite a bit of work into fusing the encoder and decoder properly in the usual way. And so some result here. So you can see that there's these two videos that get blended, and then there's some audio signal that controls the output. So now I'll put the sound so that you can hear. Try again. Yeah, girl. So the sound comes from the girl playing the instrument, so the model is able to return the correct layer. So final element of the tour. So we also did a little bit of work on a supervised word translation in video. And the idea there is that the model is seeing videos from YouTube, some of them in English and some of them in French, and they're not the same video, they're different videos. For example, it may be a video of someone showing how to mix the eggs with the flour. And again, there can be some videos in a different language, for example, in French, but there's this common element, which is the video itself, the pixels that can ground the multiple languages. And we imagine this is a little bit how children, bilingual children, learn multiple languages. They see one of the parents speaking in English while doing the eggs, and then later at a different occasion they see the other parent speaking in French, and they have this common video or like common visual that can establish the connection between the multiple languages. And yeah, so there is no pair data in this case. There are different videos, and it's kind of like an unsupervised problem. And so the overall idea would be to, in some cases, train with example videos in one language, and in some cases, train with example videos in other languages. And in all cases, what the model is trying to do is to put together text. We assume we have the text of what the people are saying with the video, pull them together, and pull apart text from other videos with those videos. So to learn basically an embedding that pulls together the correct text with the correct videos. And by having a shared video encoder, basically the multiple languages are brought together in this way. And we did some evaluation using visual words and retrieval, and it seems like the model is able to translate words from English to French and also other more remote languages to a good extent. Like, yeah, you can see the paper, the numbers, but they look reasonable. Yeah, so but to conclude the tour, you can see that a lot of this work we did over the years was always about architectures, about how to fuse modalities, how to handle multiple tasks, and you know, that's always in every paper quite a bit of work just doing that. And that motivates the second part of my talk, which is about the perceiver system. Yep, any questions before I explain the perceiver? If not, I'll just go. All right, so yeah, I already motivated this a little bit about the importance of making sense of many modalities with a single architecture, but you know, it is true that real-world data exhibits a variety of high-dimensional structures. Obviously, like images are very large, text can be very large, audio, proprioception. We have, you know, many bones, many tendons and muscles, and all of them have some tiny proprioception sensors. This can be very high-dimensional. And our goal in the Perceiver project is to have one architecture that can handle them all. Yeah, in a domain-agnostic way. And if you think about this domain-agnostic business, it's a little bit like the Matrix movie. You have these operators looking at these green screens, and they would see, you know, 3D structures and see events and all that just out of these bytes. So that's kind of like what we're trying to achieve. And you know, whenever or sometimes when I tell people about this idea, they would say that, oh, but you know, the visual cortex, it's highly specialized to vision, and so on. And maybe one argument is that what we're trying to do is a bit like evolution in some sense. So if you consider all the different bodies and animals that exist, you know, they all have a nervous system that makes good use of their sensors independently of whether they have 5 eyes like the praying mantis or 10 eyes like scorpions, all the way to 1,000 eyes of cheetahs, right? So nature finds a way to make sense of all these senses. And yeah, I was talking also with a neuroscientist that pointed me to this paper from a colleague of yours, where they tried rewiring the vision into the auditory system and observed that similar features as in view 1 would appear in the auditory cortex. So it seems like you know, the brain is fairly adaptive as well. Yeah, and so the one main challenge to achieve this is scaling. So this high-dimensional aspect of many of the modalities we're interested in. So ConvNets are able to scale very well to very high-dimensional inputs, but they bake in this domain-specific structures, such as the signal is 2D, or the signal is 3D, or the signal is 1D. That becomes like really baked into the architecture, making it hard to reuse the, you know, one architecture for different modalities. And transformers make very few domain assumptions, but they don't scale well to high-dimensional inputs. So let me just go through why self-attention in transformer scales poorly. So yeah, as you may know, let's say that we have these inputs. Let's say an image. I call here a byte array, a bit like in the Matrix. You have these bytes, but it's like m inputs, each with c dimensions. And yeah, for images, it may be very big, like 50,000 such inputs for a 2×4 by 2×4 image. And yeah, so in transformers, you have these tree mappings, or better said, in self-attention, you compute queries, the query matrix for each of for this byte array input. You compute the key matrix and the value matrix. And this part is fine. Scales linearly with the number of inputs. It's just a 1D convolution. The issue is when you want to compute these attention maps that are quadratic in the number of inputs. So if you have like 50,000 inputs, it's not really feasible to compute these matrices anymore. And then the final part of self-attention, again, it's quadratic. You need to multiply this attention matrix by another matrix, and the attention matrix is m squared again. Yeah, so our main idea here is to introduce a cross-attention layer that is linear in the input size m. And it looks a bit like this. So instead of computing the query matrix and creating like a m by d matrix, we create a much smaller one with just n elements, where n is independent of the number of inputs and typically much smaller. Let's say if you have 50,000 inputs, we'll be using like 500, and n equals 500. So 2 orders of magnitude smaller or more. So if you do this, then your attention map is going to be much tinier. So n by m, so no longer quadratic in n. And the same happens for your last step of self-attention as well. And yeah, now this latent array is independent of the input size. So you can build very deep networks on top of this as well. And going into more detail into the overall perceiver architecture. So we have this latent array that we initialize randomly, basically, and then learn it. It's like a learn RNN initial state. Then we do this cross attention between the inputs, let's say the 50,000 pixels and the latent array. Then we have a potentially very deep stack of transformers. Since they're now like n squared, we can build very, very deep transformers here. And then actually we iterate this process. So we let the model attend again to the pixels and produce a new latent array. And this is iterating is particularly useful if the latent array is really much smaller than the byte array. So if it's like significant bottleneck, it makes sense for the model to be able to attend again to the inputs informed by the computation it did already. And finally, if you have a very, very big model and your dataset is not as big, it makes sense to share the weights between these repeated cross attentions and basically have fewer weights and overfit less. In this case, the model becomes fully recurrent. And here we consider in this paper just classification, so we just average the latent array and then pass through a linear layer to get some logits. So that's what it is. And so while the architecture itself is fully domain agnostic, we still have a procedure for incorporating prior knowledge about each domain by basically stacking extra information into the byte array here. So for example, if you have positional information, as we always have for images and so on, what we do is we concatenate the position information as a Fourier feature position encoding with the pixels themselves. So there's that option of still incorporating prior knowledge, but directly in the inputs. So kind of externalize it from the architecture itself. Is this clear? Okay. So I can talk a little bit about results now. So if you have like a Resnet 50 on ImageNet, it gets like 77.6, but it uses this knowledge of the grid structure. A VIT model gets around the same, also uses the grid structure to get patches critically. If you try just a transformer, but on much lower resolution, because it doesn't scale very well, so the maximum you may be able to do on a standard GPU is like a 64 by 64 resolution image. You get much slower performance at 57%. Whereas with a perceiver with these Fourier features that encode position, but at the inputs, you get 70.0%. So without any convolutions or patching, directly from pixels. And you can even permute the pixels in a fixed way and recompute these results. For the perceiver, it's exactly the same, and for transformer, because they're fully permutation invariant. Whereas for the models that assume a particular grid structure, the performance degrades quite a bit. And we also try the perceiver without any positional information, where even the position is a learned embedding, and it still works quite decently at 70.9. So here we don't feed the position like the XY coordinates, nor these Fourier embeddings of the XY coordinates. Yeah, we can also visualize some attention maps. So basically what I'm showing here is the cross attention, what it's attempting to for each of the vectors in the latent array. So you can see that for the Fourier position encodings, It does this kind of like wavy attention map. And so it's also worth pointing out that we're not overlaying the attention map with the image. So if you see the dog here, it's because there's some content dependency here in the attention. And yeah, the model with learned position encoding, so where we don't feed the position at all, it's slightly different. I guess it has many more parameters and it looks a bit more noisy slightly. And yeah, that's it for ImageNet. We also tried this on point clouds, exact same model, since there's no prior knowledge in the architecture itself about grid structure or anything. It's just a matrix of inputs that comes in. It's easy to do. And yeah, compared to the baselines like ResNet and VIT, it does better. And compared to the state-of-the-art model like PointNet++, it's just slightly worse, but they also used extra augmentations and a bit more domain knowledge in the augmentation and featurization, which we didn't implement. It does decently. And finally, for multimodal data, like so we did some audio set classification. So it looks a bit like this. The videos in audio set has audio, video, and the goal is to predict multiple classes for each video. So in this case, speech, dog, animal, whimper, and so on. So we operated on 32 frame clips. And for audio, we tried either inputting spectrogram or raw audio. And we used patches for video because video has it's too high dimensional for Percival to handle for pixels. So we used in this case around 20,000 inputs or 70,000 inputs. Question? I heard some noise.
I actually have a question.
Yeah.
So in this setting where you have multimodalities,
Yeah.
do you use like different branches or you concatenate the modalities and like normalize them?
Yeah, so we concatenate the modalities at the input. We form a matrix having all the modalities. And I'll explain how this matrix is formed. Okay. Here. So if the multiple modalities have different dimensions, what we do is we add a bit of padding that acts also as a multimodal, as an embedding for that modality. So we add some code to each modality that tells, okay, this is audio, this is RGB, and so on. Okay, so let me go back. So first of all, here I'm showing the positional encoding plus the input. Let's say we had pixels, RGB, 3 values, and then some Fourier encoding of X, Y, and T. For audio, raw audio, it would be a single value plus some positional encoding of the time. And then what we do is we pad them with some modality-specific embedding such that they have the same size and we can form a matrix out of them. Yep. And in terms of results compared to the state-of-the-art, it's up there with the best method. So we get the 44.2 combining audio and video without any of this complex architectural design that, say, Attention AV Fusion does. So it's kind of plug and play. So yeah, that's it for multimodal results. And yeah, we can also visualize the attention maps for the video. So this model had 2 cross-attents. The first one is a bit pixelized for some reason. The second cross-attent tends to be smoother. And it seems to be consistent for different videos. It has the same appearance. So for each attention map kind of highlights different areas of the video or different periods, and also different colors a little bit. There's some dependency on color. Okay, I have a couple more examples. Yeah, here's a car. I think this is the last one. Okay, still have another one. So we also have like a special model that produced very interesting attention maps early on. So it did this kind of like attention map that was dynamic. So initially it would, the first, say, 30 frames of the video, it would get this kind of like, what we call it, space-time frequency detectors. But then the very last frame would be more like spatialized and more content-based. And for this model, it actually did this for all the field, for all the attention maps. So that so there's some diversity sometimes in the trained models. They may have slightly different strategies in some sense. Yeah, so yeah, I think we're 10 minutes from the end, so I'd like to reserve a little bit of time for questions and discussion. But yeah, I guess the overall theme I would like to raise is that maybe there will be less architecture work in the near future, but more general. And hopefully that way, researchers can spend more time thinking about the hard problems in AI and in perception, and less time just doing hyperparameter search. But obviously, an important question is, what are the real problems we need to solve to make progress in this area? Given the complexity of the scenes like these that I've shown, like spirits possessing people and whatnot. I mean, this is just one element in a very, very long tail of possible things that happen in videos. So yeah, any questions? I'm happy to discuss.
Maybe have more of a general question, but I guess pointing to the problems that you were talking at the beginning of the talk, and also right now, these very long, complex relationships to learn about video. Do you think that learning these skills will come from keeping on this self-supervised direction on videos, or that we need to think about maybe lower scale, very well annotated data sets and complex prediction tasks?
Yeah, that's an excellent question. So I guess there's value in self-supervised learning, right? So learning better feature extractions will likely need that. But I think there's important challenges, particularly just scaling up to very long videos. So I think all of self-supervised learning right now is operating on one image or 30 images, just capturing very low-level things like low-level motion, feature, very local features. So if you want to go to more complex understanding of characters and in across seasons of a TV show, there's a long way to go in self-supervised learning to learn that. Yeah, challenges in memory. I don't know if we have even a model that can detect an object or say a person reliably throughout hours of video. So yeah, lots of problems ahead of that. But yeah, I don't think we can supervise most of it. So definitely self-supervised learning will be important.
Thank you.
I had one question. Have you tried any of these perceiver models on very, very long strings of text?
For text understanding or generation, or
either one, just because I guess you can drastically increase the context window if you can compress the query.
So yeah, we have for BERT style approaches, it works well. So we have a paper coming up in a couple of weeks on that. We're also thinking on how to do it for generation, but there are some challenges there, especially around causality. So, I mean, most of these generation models need to have some kind of causal constraints there. And it's a bit harder with perceiver style model that basically compresses the whole signal into some latent space. So yeah, I think there's interesting research in that area.
Are there any more questions?
I guess I can ask one more question. So for the perceiver, you went over a slide that showed you learned the position encoding. So is it fair to say that there's zero image prior in that architecture?
Yeah. So that's an extreme case where we learned the position embedding. It's obviously worse than if you feed the position. But yeah, we were surprised that it still gets to 71% or so on ImageNet. So yeah, I don't think there's any knowledge. Okay, there's still some knowledge in augmentation. So we do some augmentation that.
Oh, I see.
Yeah.
Okay.
If there are no more questions, thanks, Joao, for the great talk. It was a pleasure having you.
Thank you. See you.
Thanks.